Thank you for your kind remarks. The title which has been chosen arose from intellectual kinesis between Bengt and myself in a series of emails. I feel very happy about it, although I'm rather nervous about tomorrow using prediction. John Kendrew used to say that even an expert scientist cannot predict what happens 3 years from now. Now, I'm reminded of the veracity of that remark by the commission that Franklin D. Roosevelt set up in 1937. He actually showed that, what he did was to set up a commission made up of scientists, engineers, mathematicians, and businessmen, and so forth. Tell me, he said, what can I expect over the horizon so that I can better sort of foster the common good in the nation? What's going to happen in the next 10 years? Well, they duly reported, and they made very sensible comments, but the most notable feature of their commission is what they missed. Now, he said 10 years. Well, I've extrapolated and said take 80 or 90 years. This is what you find. Now, you can be forgiven for missing out a totally new phenomenon, like fission and fusion, and the laser and the radar, although it could be argued that a perspicacious physicist could perhaps, if he knew of Einstein's 1917 paper, have predicted the possibility of a maser, and likewise a smart mathematician, had he read the work of Radon in Leipzig in 1917, would have told you, well, you can expect tomography also. But even more embarrassing is the fact that they missed two things. The fax machine was invented by a Scottish watchmaker in 1843. A few years earlier, a Welsh lawyer invented the fuel cell. So it is very salutary when I speak and I think, well, tomorrow's catalysts, there may be some that are already there that can answer some of the key questions that we need in order to look into the future of the need for catalysis. Now, my talk falls into three unequal parts. CO2 commands our attention in an all-comprehensive way. We've got to reduce the production of it. 45 gigatons of CO2 are produced every year. Half of it remains in the atmosphere. So there's a pressing, exigent need to utilize that CO2, and we need catalysts that can do that. We can also have to address the question of minimizing the production of CO2. Now, all this impinges upon the general discussion of a bio-based future, renewable energy, but not just energy, sustaining the quality of civilized life. It's not just the energy that you need and the storage of it, but you have to produce materials which are so much taken for granted, but which come largely from petroleum, from fossil fuels, that we have to think of also ways in which we can produce from solar energy and other renewable forms of energy, using the right catalysts and the right procedures, and doing it in an environmentally benign manner. Now, the third and last part of my talk, which will be larger than the other two, deals with ways in which you can design catalysts, and design them in an energetic and also in a sort of atom-efficient manner. There's great talk about, you mustn't produce a catalyst which is made of iridium, rhodium, palladium, platinum, or gold. These are precious materials. But if you can get a catalyst to work with 1 atom of gold or 1 atom of iridium, then the whole world is transformed. It's no longer such a serious matter. In fact, some of my friends in Britain, where auto-exhaust catalysts are produced just down the road from Cambridge in Royston, they tell me if I give you a sample of some of our best modern auto-exhaust catalysts, however good your electron microscope is, you would find it difficult to spot where the rhodium, the platinum, and the palladium are, because they're so small. Already they've reached that point. So this is the prospectus. Now, I have to begin with this series of quips made by Helmut Michel. Now, some of you may agree with all of these. Some will repudiate one or all of the statements. But the fact is that he is convinced that biofuel production using land to produce biofuel is really a profligate way of proceeding. And he ends up by saying the future of individual transport has to be electric. Now, it's one thing to worry about switchgrass and various other materials, that sugarcane, for example, and get bioethanol out of it, and then other materials. It's quite another, however, to take algae and to go to salt water so that you don't encroach, as it were, agricultural land. And one of my friends in Georgia Tech, Ron Chance, gave me this on the next slide. He and his colleagues working in Florida have been pretty tenacious and pretty successful in getting a huge analysis done on over 2,000 strains of globally screened candidates of algae, and making sure that by fermentation they overexpress them, and you have cyanobacteria, which then can convert CO2 that comes from a power station nearby in Florida, and water and sunlight, and you produce ethanol. And they do this. If you look them up in Google, you'll see that they claim this can be done. Gallons of ethanol can be produced for $1.30. Now, I'm not a businessman, and it may be that that sum is made in a somewhat tendentious way, but at any rate, that's a very impressive figure. Now, they have these proprietary cyanobacteria. These are the kind of photobioreactors that they have, and the energy efficiency, etc., very low carbon footprint. So this is good news. And furthermore, spent algae are processed into green crude that can be refined to diesel, gasoline, and jet fuel using the kind of catalysts, which I'm going to come on to later, that have been standard in the petrochemical industry for decades. Now, CO2, as I mentioned earlier, is present in superabundance. We need reactions that can take CO2 as a feedstock. We want to be able to change an irritating waste to a beneficent feedstock. And there are many. There are at least 100 reactions which organic chemists know, and I've only just got a small subset of them here, which do consume CO2, but many of the catalysts that have been designed for that are homogeneous, and many of them are quite inefficient. Nevertheless, they are useful, and polycarbonates and various other things can be made this way. But it comes nowhere near consuming the massive amount of CO2 that is generated anthropogenically, as it were, every year. Here's a simple reaction described in Chemistry World a couple of months ago. Two scientists in Imperial College found a nice method of taking cyclohexene oxide and carbon dioxide and producing this polycarbonate. So just one simple example. Now, about 18 months ago, the Royal Society of Chemistry asked me to make some introductory remarks to an international conference devoted to solar fuels and solar energy. And Harry Gray and Don Nacero and Sun from Stockholm and all the major giants were there. And I agree to do so. And then out of naivety and I suppose ignorance, I realized that the amount of solar fuels that are being produced compared to what is needed in the future, in the not too distant future, is pretty small. And this article explains why I say that, but I'll comment a little later on some of the things that I've said in that article. But nevertheless, I don't want to be too pessimistic. There are some smart people around. The Spanish group, after pertinacious work, found that nickel, supported on silica alumina, could reduce CO2 to methane by hydrogen. Now, Cox and Nocera and others, this is a nice paper in PNAS about a year ago, in which they combine a photovoltaic system with an electrochemical system for water splitting, and they have 10% efficiency. There's more description of this, and I must say, I admire the arcane language here. I'm not quite sure I know exactly what that means, but at any rate, it's a very attractive and very good, very interesting article, which deals with ways in which you can generate electricity, for example, in a delocalized manner, so that every individual on Earth in an ideal world could benefit from solar energy for that purpose. Now, there's a group in Toronto which has published a very interesting paper recently using this rather esoteric solid, which is a non-stoichiometric mixed oxide, based on the structure of a mineral which is well known in Utah, Bixbyite, which is a mixed oxide of iron and manganese. And one of its characteristics, like perovskite, is that it is easily rendered non-stoichiometric. So you have oxygen vacancies. Now, 10 or 20 years ago, my friend Wynne Roberts and Hayo Freund published a much ignored paper, which is now coming back to its own, in which they pointed out that what you need in order to be able to generate good catalysts that can turn over CO2 is to have a plethora of vacancies at the surface. And Ozin and his co-workers are full of optimism as to the kind of studies that they can carry out in future which will convert carbon dioxide to carbon monoxide. Ozin talks in very convincing terms about having a solar refinery. But he doesn't necessarily mean that he'll be producing sort of octane or isooctane. What he's saying is that we can certainly produce the feedstocks for the Fischer-Tropsch reaction, or for the water-gas shift reaction, or perhaps for the ammonia synthesis reaction, by using solar light. Well, now, that's not my area of speciality, but I felt it was incumbent upon me, talking about tomorrow's catalysts, some of them, desired or possible. Now, just to remind ourselves, I mentioned in my abstract that catalysis is the backbone of the chemical industry. And this is a pretty eloquent demonstration of why I say so. This was produced by BASF about 10 years ago, and it's not quite up to date. And many people in the audience could tell me that the biocatalysis contribution is significantly bigger than 3% now. But at any rate, as you can see, 85% of all industrial processes, chemical processes, use catalysts. And 80% of that are heterogeneous catalysts. And the majority of the heterogeneous catalysts are zeolitic. They're nanoporous solids. And I'll say quite a bit more about those. Now, just to put things into perspective, a barrel of oil is 42 gallons. It gives you 1,700 kilowatt hours. That's what we've got to bear in mind when we talk about solar fuels. Now, there are 400 petrochemical oil refineries scattered throughout the world. Some of them are massive. This one in Venezuela treats some 940,000 barrels, this is spelt in a dyslexic way compared with that, I'm sorry, per day. And I'll tell you how it happens. They cycle a fluidized catalytic cracker, and I'll describe to you the catalyst in a moment, between the reactor itself and the regenerator, where you burn off some accumulated coke, which spoils the catalytic active center, burns off the accumulated coke. 5,000 tons of lanthanum zeolite Y passed per 24 hours, and that lasts for 2 or 3 hours before you have to recharge it. That's a pretty impressive, colossal turnover. Now, here's the catalyst, and it is the product of very simple solid-state chemistry. My colleagues and I did a neutron diffraction study of the structure of lanthanum zeolite Y about 25 years ago. Now here's the mineral. It's a very rare mineral. There's a kilogram or so that you can mine in Bavaria. But it's so very easy to produce kilograms for a few cents, using a method that Richard Barra in Imperial College and many of the oil company scientists developed in subsequent years. And so you can replace all the ion exchangeable cations with lanthanum. Now I'm showing you two sort of schematic drawings. This is the polyhedral one. Here's the actual structure. The lanthanum is inside the supercage. The opening to the supercage is 7.4 angstrom units. So the 60 or so components of heavy oil, about 2/3 of them can enter and be processed. But the large ones, the heavier oil, can't enter. That because the opening, the aperture is not quite large enough. I'll come to ways in which we can enlarge that in a moment. But here are 2 key points. Bengt, I think, mentioned in a question that arose this morning about polarization. You see, the great merit of a small ion, which is triply ionized, lanthanum 3+, is that it so tenaciously hangs on to the last water molecule of hydration that it doesn't give it up even as you heat. Instead, it gives you cation hydrolysis. So for every lanthanum, you leave a sort of loosely attached proton. I've indicated one of them there, but there are 6 different equivalent sites. But this was the neutron diffraction study done at liquid nitrogen temperature. The other point about the lanthanum is that it pulls in and strengthens the structure. Now this is a fluidized catalytic cracker. Chemical engineers know that you can't use catalysts unless they have attrition resistance. And the fact that you have the lanthanum there, or any rare earth element, or any triply charged ion there, will help retain the integrity of the actual catalyst itself. Now here are some of the products of petroleum refining. This slide was given to me thanks to my appearing at a Molecular Frontiers conference which you'd organized 2.5 years ago at Jay Kiesling from Berkeley, put on this screen, and thou shalt not covet thy neighbor, whatever it is in the Bible, thou shalt not covet thy neighbor's slides. Well, I did covet it, and I've been using it ever since. And, you know, fuels, fabrics, pharmaceuticals, and so many other things. Just look at that, toothpaste and CDs. You can't have civilized life without petroleum refining. It's a fundamental fact. So when we talk about a bio-based economy and renewable energy and renewable materials from the wind or the sun or the air or whatever, this is what we got to target. Now, let me turn, I've said enough about catalytic cracking. Now let me turn to ammonia synthesis. Fritz Haber was able, after playing around with osmium, to get his hands on Swedish magnetite from, I don't know if I pronounce it correctly, Bengt, but is it Gällivare? Is it? Gällivare, whatever. And that happened to contain just the right tincture of impurities, which promoted the catalyst and stabilized it. And for 70 years or so, the ammonia synthesis catalyst, well, 700 million tons of ammonia are produced per annum. But for the last 15 years, it's the BP catalyst that is used, the ruthenium catalyst, whenever they set up a new reactor. I was partly involved in the process as a consultant at the time, and this picture was taken by one of my PhD students. It's in fact some calcium or rubidium or potassium in contact with graphitized carbon. And that is an extremely good catalyst. Now, this is an interesting plot which was given to me by Gerhard Ertl. This is the way in which human population, this is how ammonia production has gone hand in hand, as it were. Now, in view of the interests of brevity, I won't mention many of the other things, but all the molecules that I'm talking about, you know, they amount to 100 or 200 Daltons. I'm not talking about kilodaltons or megadaltons. These are very simple things that I'm concerned with. But one particular reaction which I want to draw to your attention, which Haber and Mittasch and Bosch in BASF very early on realized was vitally important, because carbon monoxide poisons the iron catalyst in ammonia synthesis. So you need a method of weaning away any traces of carbon monoxide, and the way to do it is by the water-gas shift reaction. It forms CO2, but it's a lesser of two evils. Now, the interesting thing is that there's a group, Flitzani Stephanopoulos, she and her colleagues in Tufts University have just published in JACS an extremely interesting paper. It's a sequel of several other papers that she's been publishing over the last 5 years or so, in which she's been using nanoparticle gold to begin with, only to discover that contrary to accepted dogma, as it were, the nanoparticle gold wasn't really participating in the reaction. She thought that it was a few small particles or a few small clusters of gold anchored through a chemical bond via an oxygen to the substratum that really was functioning as the catalyst. Well, this is the paper that she's just published. She's using 3 different kinds of support. And she finds that platinum in the 2 oxidation state is bonded to oxygen and OH and is also stabilized by 6 sodium ions. But here they are, individual single platinum atoms. On a TiO2 support, you can see the lattice fringes. On the zeolite potassium Kl support, and on the MCM, mobile catalytic material, it's the silica. It's overwhelmingly clear that single atom catalysis is doing well. Now, the reason why she talks about a common single site, it has been, again, thought largely as a result of the ingenious work of Jens Norskov, now in Stanford, formerly in the DTU, that depending on the nature of the support, whether it was magnesium oxide or shall we say aluminium oxide, which he regarded as being non-reactive or non-reducing, in contradistinction to the way in which supports made of iron oxide or ceric oxide were concerned, they behave differently. Now, ceric oxide is a fundamentally important support material in the auto-exhaust catalyst because it feeds oxygen when it's needed, but it's also an important support. Now, I just thought I should remind you of how we tell whether we can get, by high-angle annular dark field. That's the way we measure these individual atoms. And the way to do that is by this method. You have a scanning transmission electron microscope. You can have forward scattered and Bragg scattered electrons, or Rutherford scattered electrons, which go through a much higher angle, and that's dependent on the atomic number of the material that you have to the power of 2. And that's why it's very easy to pick out things like individual atoms or clusters of bismuth, for example, which my postdoc, Rowan Leary, has done in Cambridge. This is crystalline bismuth, and these are sort of ablated material. Now, this mixture, Ka oil, of cyclohexanol and cyclohexanone, 3 million tons of that are produced per annum in the United States alone. Why? Because they can give you cyclohexanone, which is the starting point of nylon 6. And about 6 million tons of nylon 6 are produced per annum. Now, it so happens that in that mixture, it's an azeotropic mixture, it's very difficult to separate. But my colleague, Robin Raja, has found a method where we use minute platinum particles, nanoparticles, where we can, with oxygen alone or air, convert the cyclohexane to cyclohexanone, which is a big step forward. Now, here are some other examples which have come from China. 2 very prominent papers from China recently. Remarkable performance of iridium-1 in water gas shift, and platinum single atom and pseudo single atom catalyst for functionalized nitroarenes. The dyestuff industry needs a huge number of amino aromatic compounds, and they have shown in Dalian and other places in China how to do that in a very simple, straightforward, benign way using single atom catalysts. Now, I've always been interested for the last 10 years or so in single atom catalysis, and I now want to spend the remainder of my time talking about nanoporous solids with well-defined pore structures, controllable diameters, they're easy to prepare, from a small diameter of 3.5 to 500 angstrom, fashioned into heterogeneous catalysts with single type of spatially well-separated, well-defined sites, active sites. And these can be introduced either during synthesis or by post-synthesis modification. Now, the good thing about these is these nanoporous materials are effectively 3-dimensional surfaces. So it's very easy, and you need a high area to get catalytic efficiency anyway, but you can place dexterously and very delicately and define precisely by X-ray absorption and various other techniques precisely what the nature of the active site is. Now, just to remind you, here's silicolite, ZSM5 or TS1, which is used extensively already by the Anychem company. These large white spots are 5.5 angstrom units. Here's zeolite beta. Now, aluminosilicates occur naturally, and they're very robust, and they can maintain being heated to 900 degrees centigrade, usually without demur. Aluminium phosphates, which were first devised in a nanoporous form by the Union Carbide Company, of which there are about 50 different structures, Alpo 5, Alpo 36, Alpo 44, Alpo 31, Alpo 18, etc. They're terrific things, and what is more, all these elements and a few others can be inserted into the framework. These are not cations which are separate in order to preserve electron neutrality. They can be inserted into the actual framework. Now, these are tomograms of MCM41. This is silica. The diameter is there about 30 angstrom units. And all these silicas have silanol groups which are readily functionable. Now, two Spanish gentlemen working separately, one who used to work in the Royal Institution in my group in Alicante now, Garcia Martinez, and Ramirez, here they are, he's in the ETH. They've found methods, very simple but very ingenious, and it works beautifully. They convert microporous zeolite into a mesoporous zeolite, and they do so by playing around with micelles. Here's a typical micelle, which can be inserted into the framework at growth, at synthesis, and then that can be burnt off, and it leaves behind a nice open gap. And depending on the length of the micelle chain, you can have a bimodal distribution, you can have a 50 angstrom unit diameter. So then that's very open. And now you can go deeper into the oil barrel to process those materials. You can handle much, much bigger molecules. That's been a major breakthrough in the last 5 years or so. Here's a gallery of some typical microporous zeolites which I've played with. This is zeolite mobile, number 5. This is theta 1, which was discovered and designed in British Petroleum. This is Davy Faraday, number 4. Davy Faraday, number 1. Faugesite, Alpo 5, Alpo 36, beta. You can see you go from 5 angstrom units right up. You can start from 3.5 and go right up to about 8. Now, Jean-Marie Lane mentioned, although he didn't actually use the term, metal organic frameworks, but these are very important and becoming more so. There are about 35,000 structurally different MOFs now known, and the number is likely to continue to increase. This is Hong Kong University of Science and Technology number 1. That came on the scene about 12 years ago. This is Stockholm University number 5. And this is MOF399 from Berkeley. And look, 38 angstrom units. And this one is from Lavoisier's laboratory in Paris, and this is from the Royal Institution. Now, the great thing about these is you can, in fact, use them as templates to make nanoporous oxides. It's been done in Penn State University. You can get brookite, TiO2, in a nanoporous form. Now, here's Alpo 5. The great thing about Alpo 5 is if I replace aluminium with cobalt-2, I form a Brønsted acid site. Here it is, another one there. If, however, I put cobalt-3 in, that's a redox site. So now you can see an infinite scope for change that you can play with here. You can have a monofunctional Brønsted acid catalyst, or a monofunctional redox catalyst, or a bifunctional catalyst. And this is just Alpo 5. Well, here's an exemplar of single-site heterogeneous catalysts. Here's ZSM5, here's the sort of pictorial picture. You see how far the detached protons are. Here's the active site. Here's a simple reaction. You can take glycerol, which is produced in superabundance along with bioethanol, and convert it with 100% efficiency and selectivity to acrolein. And if you titrate this acid catalyst with pyridine, you come to a sort of all the sites are of similar energy. Now, if you want to make a mesoporous catalyst, where you have a larger pore of silica, this is a way in which you may do it. We were trying to produce a titanium epoxidation catalyst. You start with titanosine dichloride, which you sequester into the large pore. And then you gradually sort of graft it onto the scene, as indicated here. You follow the X-ray absorption, and you end up having gone through this half sandwich compound, which makes sure that the atom centers are far apart, and then you have these isolated catalyst centers. Now, epoxidation with titanium is very easy when you have hydroperoxide. Here's the 4-coordinated. Now it's 6-coordinated. In comes the cyclohexene oxide, takes out. This mechanism was proposed by Dan Ely when Ely was 22 years of age. 6 months ago, he celebrated his 100th anniversary, and he was very, very pleased to know that his mechanism has been sort of corroborated repeatedly by so many other things. Now, very quick word about being able to have regioselective catalysis by choosing one active site per cage, as I've done here. Now, the alkane can only enter in one way, head first, as it were, and meets the active site. Now, bear in mind that the Barton challenge, which is quite a considerable one, asks you to be able to distinguish, to oxidize preferentially a CH bond which was stronger when it is in CH3 than it is in CH, as in there, 91 and 95. Well, by designing 2 sites per cage, we were able to do that, but not quite to the same efficiency as John D. Roberts wanted in order to award a prize for the Barton challenge. A very quick word about the industrial process that is used on a massive scale to produce nylon 6. You take cyclohexanone, you have a hydroperoxide, hydroxylamine, sulfate, I beg your pardon. That forms the oxime. You then use oleum. You form caprolactam, you get the Beckmann rearrangement, you heat that, and you get nylon 6. Our alternative process just takes ammonia. In air, it forms NH2OH, in situ production of hydroxylamine. This molecule is small enough to go in there. It can then pick up one of the protons and go and form the oxime, and you heat that. So you do that in one step. So here's a proof of principle of how you can do this. We published that 10 years ago. It's now taken on a fresh significance. This is the scale in which cyclohexanone oxime is produced. A single site method can generate the oxime with 100% selectivity, and there are commercial sites now operating in China and in India. One word about epoxidation of renewable feedstocks like fatty acid methyl ethers or various types of terpenes. You can generally produce these epoxides with very little effort under benign conditions. And the MOFs can be used very ingeniously, as my former student, now a professor at St. Andrews, has shown, by putting scandium in there, which is a very strong Lewis acid, following an example in a homogeneous solution of the work of David Evans, you can carry out CC and CN formation, which is not an easy thing to do. But you can do this heterogeneously very easily. Now, zeolites are not generally chiral. Only 5 out of the total 260 that's known are chiral, and they're not very promising. This is the Stockholm University number 32. This is Oslo. This is from Mobil company. This is from Valencia. And this is a natural zeolite beta. Now, unfortunately, you can't use the sort of chirality of the structure to carry out enantioselective reactions. But what you can do is play tunes with a mesoporous solid, and you can put in a chiral ligand, and the substrate can enter, the pro-chiral substance can enter, and you can carry out asymmetric work. In the interest of time, I can't dwell too much except to say that we've carried out several different reactions. I'll skip that, and I'll also just show you this. Harry Gray mentioned after Roger spoke, why don't you use platinum carbonyls? Well, we used bimetallic carbonylates with an organic cation, and we could get rid of the organic cation and just heat them. We could get monodisperse, these red dots, and monodisperse 1 nanometer diameter bimetallic catalysts, and they are very, very good for hydrogenation, extremely efficient, with turnovers of about 10 to the 5 per hour. Well, these are the energy levels. Here are some examples of the kind of nano cluster materials. You can take muconic acid, which occurs in nature. You can produce it to generate adipic acid. That's another method of doing it. Here's an example of the teeming number of nano clusters that you have. This shows how we know the bonding. This is the penultimate slide. I just want to show the fact that in industry, when you want to prepare this linker molecule for polymer industry, cyclohexane dimethanol, it's done in 2 separate steps, which are very demanding. Look at them, 2 separate steps. By using a cluster like this, you can do it in one go. That's not something that's commercial as yet, but we wanted to show proof of principle. Well, in summary, the single-site heterogeneous catalysts, as my colleagues and I have been working for the last 15 years or so, enable us to do all sorts of reactions, ammoximation of cyclohexanone, the Beckmann rearrangement, selective isomerization, doing some asymmetric reactions, synthesis of gasoline using propane and butane. This is used in fracking at the moment. All these things in color are now either already commercialized or on the road to being commercialized. The terminal oxidation of alkanes, and the aerobic shape-selective oxidation of cyclohexane, bio-Villiger conversions, conversion of bioethanol to ethane, methanol to ethene and propane, formation of niacin, which is a very important vitamin, selective oxidation of toluene, epoxidation of fatty acids, nanoclusters, etc. Now, it's illusory to think that our technique of strategic method of getting at catalysts can perhaps be addressed to the ammonia synthesis catalyst. But the fact is, it is very useful, especially in the context of, say, what Frances Arnold might well tell us when she speaks later in the week. From glucose, she hijacks the system and produces isobutanol. Now, isobutanol is a very good gasoline substitute anyway, but with ZSM5, that's a single-site heterogeneous catalyst, you can produce jet fuel and various other products, and all sorts of oligomers and various other derivatives which come from a bio world, as it were. Well, corn, as she said to me a short while ago, is expensive and oil is cheap, so this is not being done in a big way at present. However, the principle is there. Sugars derived from biomass can be fermented with one or more species of microorganisms, and therefore you can produce a large number of alcohols, and you can generate materials of the needed in civilized life. I'm sorry if I've overrun my time. Thank you very much for your attention.
Thank you so much. Thank you.